In this video, I want to talk about Cayley's theorem. In the very early days of modern algebra and abstract algebra, a group always meant a group of permutations. These were the only kind of groups that mathematicians used. And about 100 years ago, the mathematician Arthur Cayley discovered that every group is actually isomorphic to a group of permutations. So roughly, this means that the groups of permutations are actually all of the groups that we have. Every group is either a group of permutations or a carbon copy of a group of permutations. And this is actually one of the most classic theorems in modern and abstract algebra. So Cayley's theorem says that every group is isomorphic to a group of permutations. And this is kind of a long proof, but we'll go ahead and walk through the steps. Let's let G be a group. We want to show it's isomorphic to a group of permutations. The first question may be, what group of permutations is this isomorphic to? What are we permutating? What set do we have our permutations on? Well, as of right now, the only really set that I have is G. So I'm going to look at permutations of my set G. For every element A in G, I'm going to define this function pi of A that goes from G to G, defined by pi of A of x is equal to A of x. So in other words, this is a function that multiplies on the left by A. So the first thing I want to show is that pi of A is a permutation. A permutation is a bijective function from G to G, so I need to start by showing it's injective. Let's let pi A of x1 be equal to pi A of x2. Then I have that ax1 is equal to ax2 by definition of pi A. Multiplying both sides on the left by A inverse then gives me x1 is equal to x2. So we do have that this is injective. Next, we need to show it's surjective. Let's let y be an element of G. Then pi A of A inverse y is equal to A inverse y, which is just equal to y. So I took an element in my output set and showed that there is something that maps to it. Therefore, this is injective. So now I have a bijective function from G to G, which means it is a permutation on G. It's important to remember this is not a single permutation. I have a lot of permutations. I have one for every element in G. So I'm going to let G star be the set of all of these permutations. This is not all of the permutations on G, but it is a set containing some of the permutations on G. Therefore, I need to show G star is actually a subgroup. In order to say that it's isomorphic to a group of permutations, I need this to be a group. So we need to show this is a subgroup of all of the permutations of G. The first thing we need to show it's a subgroup is that it's closed under the group operation. So pi A composed with pi B is equal to pi of AB. In order to do this, we have to show that it has the same effect on every element. So the way we need to show this is that pi of A composed with pi of B of x is equal to pi AB of x. Well, pi of A composed with pi of B of x. This is the same thing as saying pi of A of pi of B of x. Well, pi of B of x means multiply on the left by B. Pi of A means multiply on the right, or on the left by A. I do have associativity, and now this gives me pi of AB of x, since now I multiplied x on the left by AB. So it is closed with respect to composition. The next thing I need to show is that it's closed under inverses. Let's consider pi of a composed with pi of a inverse. By what I just showed, this is the same thing as pi of a inverse, which is the same thing as pi of the identity. So this tells me that the inverse of pi of a is equal to pi of a inverse, which does show me that this is closed with respect to inverses. So now I have that G star is a subgroup of the group of all permutations on the group. So now I only have one thing left. I found my permutations, I proved they could form a group, and now I need to show that that group is isomorphic to my original group G. I'm going to define my function f going from G to G star by f of a is equal to pi a. And I'm going to claim this is my isomorphism. Let's start with injective. If f of a is equal to f of b, I need to show that a is equal to b. Well, then pi of a applied to any element, like my identity, should be equal to pi of b applied to the same element, the identity. Well, this would mean a times the identity is equal to b times the identity, or a is equal to b. So we have shown that it is injective. Let's show surjective. So let's let pi of a belong to G star. Then we have f of a is equal to pi of a. So it's very easy to see surjective. Finally, I need to show my identity. Let's look at f of ab. This is pi ab. We showed previously that that's the same thing as pi of a composed with pi of b. So this is the same thing as f of a composed with f of b, which shows that my identity must be true. So now this is an isomorphism, and I showed my group was isomorphic to a group of permutations. Let's show that D3, my symmetries on a triangle, are isomorphic to S3. And in order to do this, I'm going to go ahead and form my group, or my function. So let's say I have a triangle. Let's call this 1, 2, and 3. Let's look at rotating this once clockwise. Then relabeling my vertices, I have 1 that moves down, 2 moves to the left, 3 moves up. So my 1 vertice turned to a 3, my 3 turned to a 2, and then 2 turned back to a 1. So I can see how I got that permutation. If I were to do r squared and rotate this twice, this time we have 1 at the bottom left, 2 at the top, and 3 at the bottom right. So now from my original triangle, 1 moved to 2, 2 moved to 3, and 3 moved back to 1. So there are 2 of my permutations right there. And now I just need to consider my flips. I will not show them, but I highly encourage you to go ahead and draw your lines of reflection here and see if you can figure out the corresponding permutations. Once we have that, that gives us our bijective function, and we then need to prove that the group operations hold, that f of ab is equal to f of a, f of b. In cases like this, where it's a little bit harder to give a direct function with a nice equation, it would be helpful to build group tables for both of these and show that it is the same group table. So I highly encourage you to do that on your own.